In the last video, we discussed a special class of coordinate systems called the Lorenz gauge, where the Einstein tensor in linearized gravity reduces to a single term involving the D'Alembert of the metric perturbation h bar. Taking the case of a vacuum, where the energy-momentum tensor is zero, the Einstein field equations reduce to a wave equation for the metric perturbation, which describes gravitational waves. In this video, we're going to use a special coordinate system called the Transverse-Traceless Gauge to show how gravitational waves have two polarizations, the plus and cross polarizations. The term polarization refers to the geometric orientation of waves. For example, the electric field in electromagnetic waves can oscillate vertically, which is called vertical polarization, or oscillate horizontally, which is called horizontal polarization. These two polarizations combined together in different amounts and different phases can give rise to other polarization types, like diagonal polarization or circular polarization. Now, electromagnetic waves are oscillations in the electric and magnetic vector fields. So polarization basically just means the direction of the vectors. But gravitational waves are oscillations in a metric perturbation. And so polarization refers to how the distances between objects change in different directions. Gravitational waves have plus and cross polarizations, which are two different ways that the distances between points can oscillate. In linearized gravity, all gravitational waves are combinations of the plus and cross polarizations, combined together with different amplitudes and phases. So we know that in linearized gravity, the metric g can be written as the flat metric eta plus a small perturbation h. This h perturbation has 16 components. So it's worth asking if there are maybe 16 different types of gravitational waves that can propagate through spacetime. In this video, we're going to see that there is a choice of coordinates where the 16 metric components reduce to only two independent components, which correspond to the two polarizations of gravitational waves, the plus polarization and the cross polarization. The coordinate system where these two independent components are most obvious is called the Transverse-Traceless Gauge, or TT gauge. And remember, physics doesn't depend on our choice of coordinates. There are only two polarizations of gravitational waves, regardless of our choice of coordinates. But in many coordinate systems, this is difficult to see because the components of H have very complicated relationships with each other. The TT gauge makes it obvious that there are only two polarizations. So we know that in the Lorenz gauge coordinate system, in a vacuum, the Einstein field equations tell us that the h bar components satisfy the wave equation, where h bar is defined here. The most straightforward solutions to the wave equation are plane waves, where wave peaks come in spatial planes with constant spacing that are infinite in extent. While it's true that plane waves are a very specific type of wave, since the wave equation is linear, any generic wave can be written as a linear combination of plane waves of different frequencies. In flat space-time, a plane wave is written as an amplitude times a cosine. We can also rewrite the coefficients with a sum with the Minkowski metric, or rewrite it as the real part of a complex exponential. So in this video, I may write plane waves as complex exponentials for convenience, but the true gravitational wave is just the real part. These k coefficients, when written with upper indices, are the components of the wave vector. And when written with lower indices, they are the components of the wave covector, which we discussed in Relativity 106a when we talked about relativistic Doppler shift. The xyz components of k are the angular wave numbers, and the time component is the angular frequency omega divided by the speed of light c. Division by c gives the angular frequency the same units as the angular wave numbers, and also cancels with this c in the ct time component to give an equivalent plane wave equation. Given a plane wave on a space-time diagram, the wave covector k represents a stack of surfaces that line up with the wave's wavefronts. The components of the covector measure the density of the stack surfaces in the space and time directions. The corresponding wave vector k is a vector that points in a direction orthogonal to these surfaces, where this is the Minkowski or Lorenz definition of orthogonal, so the direction of the vector is reflected in the diagonal line representing a beam of light. So when we compare the directions of the covector surfaces and the wave vector, they are mirror images of each other reflected along a diagonal line that represents a beam of light. Note that the spatial components of the wave covector have the opposite sign compared to the spatial components of the wave vector. This is because the spatial orientation of the wave covector stack is reversed compared to the spatial orientation of the wave vector. So the spatial wave covector components with lower indices and the spatial wave vector components with upper indices have opposite sign. In flat spacetime in Cartesian coordinates, we change between the raised and lowered indices using the eta metric. And more generally, we raise and lower indices with the generic g metric. Since gravitational waves are oscillations in the 4x4 symmetric metric perturbation h, the amplitude for gravitational plane waves is also a 4x4 symmetric matrix, where we can swap the two indices and get the same value. To review waves a little more, let's recall what happens when we take the derivative of a plane wave in the alpha direction. Since the a amplitudes are constant, we take them out of the derivative. And since the derivative of an exponential is just itself, we leave it alone and just get a chain rule term on the end. The complex I is constant, and the wave covector k for a plane wave is constant, so we just get partial x sigma by partial x alpha. This goes to 0 unless sigma and alpha are the same index, so we get a Kronecker delta, which turns this sigma index into an alpha. So taking the derivative of a plane wave just gives us the original plane wave times the complex I times the wave covector component in the direction of the derivative. Since gravitational waves travel at the speed of light, this wave covector k must be a null covector, also called a light-like covector, meaning its squared magnitude is 0. To see this, we start with the wave equation on h bar, and expand the D'Alembert operator so we get two partial derivatives on h bar. These each give us a factor of the imaginary I times k. I times I gives -1, and the metric can be used to raise one of the indices on k. Since all of this is equal to 0, we're forced to conclude that the squared magnitude of the wave covector k must also be 0. So the wave covector, or equivalently the wave vector, both have a squared magnitude of 0, so they are null or light-like. So given this wave equation, the amplitude A has 16 components. As I said at the start of this video, there are really only two independent components. So let's see how we can narrow down these 16 components down to two components. First, since gravitational waves are waves in the metric, and the metric is symmetric, the A matrix must also be symmetric. This means that 6 of the 16 components are redundant, so there are really only 10 independent components. If we choose to look at plane waves in the Lorenz gauge, this will further reduce 10 to 6 independent components. If we're working in a Lorenz gauge coordinate system, this Lorenz gauge condition must be true. This beta derivative acting on the plane wave gives a factor of I times k out in front. And this forces us to take k summed with the amplitude A to be 0. Basically, this means that the columns of the amplitude matrix A must be orthogonal to the row of wave covector components k. If we use the metric to raise and lower indices, we can get an equivalent formula with the wave vector k with upper indices, and the amplitude matrix A with lowered indices. This constraint of A summed with k giving 0 gives 4 constraint equations on the components of A, which reduces A from 10 to 6 independent components. Now recall, the Lorenz gauge is not one unique coordinate system. It's really a class of coordinate systems. If we take some coordinate system in the Lorenz gauge, then apply some displacement field chi, where chi satisfies the wave equation, the resulting new coordinate system will also be in the Lorenz gauge. So we have the freedom to pick one specific Lorenz gauge coordinate system from all of the Lorenz gauge coordinate systems. We can use this freedom to reduce the number of independent A components from 6 down to 2. In particular, we will use one particular Lorenz gauge coordinate system called the Transverse-Traceless Gauge, where the two polarizations of gravitational waves become very obvious. Since we can invent a 4-component displacement field chi that keeps us inside the Lorenz gauge, we have 4 degrees of freedom that we can specify without leaving the Lorenz gauge family of coordinate systems. Since the displacement field ultimately determines the metric perturbation h bar, this means we also have 4 extra degrees of freedom on h bar, or equivalently the wave amplitude A. So we can define 4 more constraints on the wave amplitude A. 3 of these will be transverse constraints, and one of them will be the traceless constraint. Let's start with the 3 transverse constraints. Let's take a space-time observer with a 4-velocity vector u, who is experiencing gravitational waves. In theory, the gravitational wave could be passing by our observer at any angle. But since we have 4 degrees of freedom, we have the freedom to choose coordinates where the wave's oscillations are at right angles to the observer's world line, with right angles also being called orthogonal or transverse. Mathematically, we express this by saying the summation of the wave amplitude A with the observer's 4-velocity u is 0, expressed in matrix form here. Now, you might look at this formula and think that there are 4 constraints here, since there are 4 equations. But there are actually only 3 new constraints here. This equation with the wave vector on its own gives 4 constraints, and this equation with the 4-velocity on its own gives 4 constraints. But together, they have one shared constraint. So between the 2 equations, there are 7 total constraints, not 8. To see why, imagine picking a 4-velocity vector where only the time component is non-zero. This results in all the A components with a t in the second index going to 0, which also causes the A components with a t in the first index to go to 0 as well, since A is symmetric. Because of this, the wave vector constraint now only gives us 3 meaningful equations, since the time equation is already satisfied for free because any A component with a time index already equals 0. So this equation now only gives us 3 new constraints instead of 4. And the reverse is true as well. If we start with the wave vector equation and get 4 constraints, then the 4-velocity equation will only give us 3 new constraints. So in the Lorenz gauge, the transverse condition, which requires that gravitational wave oscillations be orthogonal to a 4-velocity vector, only gives us 3 new constraints. The last constraint is the traceless constraint, which means we take the amplitude matrix A to be traceless. Remember, this involves summing an upper index of A with a lower index of A, where one of the indices is raised with the inverse metric. So starting in any Lorenz gauge coordinate system, we pick out a specific Lorenz gauge coordinate system called the Transverse-Traceless Gauge by defining 4 constraints on the wave amplitude A. 3 of these constraints come from requiring that the wave oscillations are transverse to an observer with a four-velocity u. And the 4th constraint demands that A be traceless. And since the wave amplitude A sits in front of the plane wave formula, we can also rewrite these constraints with h bar instead. So these conditions define a specific Lorenz gauge coordinate system called the Transverse-Traceless Gauge. And these 4 constraints reduce the total degrees of freedom on our wave amplitude down to 2. Now recall that the formula for the h-bar components involves the trace of h. If we sum all terms in the equation with the inverse metric, this will raise indices on h-bar and h, and also cancel with this metric to give us a Kronecker delta. This becomes the trace of h-bar, this becomes the trace of h, and the trace of the Kronecker delta in 4-dimensional spacetime is just the trace of the 4x4 identity matrix, which is 4. Simplifying this equation, we get that the trace of h-bar equals the negative trace of h. Now we know that in the transverse-traceless gauge, the trace of h-bar is equal to 0 by definition. And by the formula we just proved above, this also means the trace of h is 0. And if we set the trace of h to 0 in our original formula, this shows us that in the transverse-traceless gauge, h-bar and h are the same thing. So in the transverse-traceless gauge, anytime we've written h-bar, we can just replace it with h, which is just the original metric perturbation without any modification. So let's review the constraints on the components of the gravitational wave amplitude A. First, it must be symmetric. Also, if we use the Lorenz gauge, it must satisfy this set of 4 equations with the wave vector k. Also, in the transverse-traceless gauge, it must satisfy this set of equations with a 4-velocity vector u, and also be traceless. To take advantage of these constraints, we actually need to pick a 4-velocity vector u and a wave vector k. We'll take the 4-velocity vector to just be the time basis vector et, multiplied by the speed of light c, since the 4-velocity vector always has a magnitude of c. So the time component is c, and all the spatial components are 0. For the wave vector k, we'll take a wave propagating only in the z direction. So its wave numbers in the x and y directions are 0, and its frequency in time and its wave number in the z direction are equal to each other, as required for a null covector with a 0-squared length. So right away from the constraint involving the 4-velocity, since all the components of the 4-velocity are 0 except the time component, all terms in this summation go to 0 except for the term involving the time component of the 4-velocity, which is the speed of light c. This forces all of the A components with t in the first index to be 0. And by the symmetry of A, all components of A with t in the second index are also 0. So all components of A containing a t time index are 0. Next, using the constraint with the wave vector, we get this summation where the x and y components of the vector are 0. We already showed that A components involving a t index are 0. So this constraint results in A components with the first index of z going to 0. And by symmetry of A, all components involving a z index go to 0. Next, since the trace of A is 0, this tells us that AXX and AYY are really the same component but with opposite sign, so they are not independent. And finally, the off-diagonal xy and yx components are equal to each other by the symmetry of A, so they are not independent either. So after looking at symmetry and all the redundancies available in our choice of coordinate system, the wave amplitude matrix A has 2 independent components, AXX and AXY. And we're going to rename these as A plus and A cross. As you can probably guess, these 2 numbers correspond to the amplitudes of the plus polarization and the cross polarization, that are present in a given gravitational wave. We'll talk about these more in the next video, but a plus polarized gravitational wave causes a ring of free particles to stretch and compress along the directions of a plus sign. And a cross-polarized gravitational wave causes a ring of free particles to stretch and compress along the directions of a multiplication cross sign. So to summarize this video, if we're looking at gravitational plane waves in the metric perturbation h-bar, we showed how we can take the 16 components of the metric perturbation and reduce them to only 2 independent components. 6 of these components are made redundant due to the inherent symmetry of the H matrix. And another 8 components are redundant because they are a result from our freedom to choose whatever coordinate system we like in spacetime. If we focus on the Lorenz gauge class of coordinate systems, and further narrow down to the unique Transverse-Traceless Gauge coordinate system, we see that there are only 2 independent components of the metric perturbation H, which correspond to the plus and cross polarizations of gravitational waves.